Last time, we left off wondering how less than 10 years after the ALV project, Dean Pomerleau and Todd Yoakum were able to drive across the entire US 98% autonomously. To get to the bottom of this, we need to visit Carnegie Mellon University in the 1980s. In 1986, a couple years after the start of the Autonomous Land Vehicle project, Carnegie Mellon built its own autonomous test vehicle, a retrofitted Chevy van they called NavLab. Just like the ALV, NavLab included a roof-mounted color video camera, and CMU researchers experimented with a variety of vision algorithms. However, by the end of the decade, it became clear that one approach, taken by graduate student Dean Pomerleau, was more robust and adaptable than the rest. And what I think is really interesting here is just how different this approach is than the ALV vision algorithm and other vision algorithms of the time. To get a sense for how Pomerleau's solution worked, let's briefly revisit the ALV, zoom out a little, and think about how the whole system worked. Last time, we discussed how the ALV team used color-based segmentation to pick out road pixels in images. These road pixel detections were then used to estimate the location of road boundaries. This information was then projected from image space to world space, and finally fed into a controls algorithm that produced a direction to steer the vehicle. Note that we're just talking about controlling steering, also known as lateral control, and leaving out the systems that controlled vehicle speed for now. Making this simplification, mathematically, we can think of the ALV system as a big function that for its input takes all the pixel intensity values from our incoming image, and for its output returns just one single number, the angle to steer the vehicle to keep it centered on the road. Now, the ALV team chose to break apart this math problem into these discrete blocks. But we could, of course, choose other ways to break apart the mapping from input images to steering angles. And generally, we can think of the process of steering a vehicle autonomously as a single big math problem, where we're trying to find some function that takes for its input our sensor data, in this case our input image, and for its output returns just one single number, the angle to turn the steering wheel. To steer a car autonomously is to find a solution to this math problem. Now, here's where it gets interesting. In 1986, the same year the NavLab vehicle was built, another group at Carnegie Mellon, led by Professor Jeff Hinton, published a paper entitled Learning Representations by Backpropagating Errors. This paper reignited interest into artificial neural networks. These mathematical models are loosely based on how our brains work, and Hinton's paper presented a new way for artificial neural networks to learn from data. Now, when Dean Pomerleau showed up the following year at Carnegie Mellon to begin his PhD, he saw an opportunity to create a dramatically different vision system for autonomous vehicles. Instead of manually programming a whole system, block by block, to map from input images to steering outputs as the ALV team had done, what if we could use an artificial neural network to learn the whole thing? Even better, in Dean's words.
And I said, why don't we just try and let the neural network figure it out? Give it an image and have it figure out how to steer by watching how a person reacts in the same situation. So supervised learning.
Let's try out Dean's idea. As Dean mentioned, his approach calls for supervised learning, which means that we need both input images and the corresponding steering angles from a human driver to learn from. We'll use a few human-driven laps of test track data to train our neural network, and save one lap to test our algorithm's performance. We'll make use of Dean's ALVINN neural network architecture. Each pixel of an input image to ALVINN is connected to 4 separate hidden units. Just as in other neural networks, each connection here represents a single number. These numbers, typically called weights or parameters, are multiplied by the pixel intensity values in our input image, and the results are added together. We'll downsample our input images to 64 pixels wide and 60 pixels tall, and here we're only going to use the blue color channel of our input images. So each of our 60 times 64, or 3,840 input pixels, are multiplied by 4 separate sets of 3,840 weights. We can visualize these weight values as images themselves. We'll use a color map to color our weight values, where large positive values are colored yellow, and large negative values are colored purple. Now, when our network learns, it makes incremental adjustments to these weights, in an effort to make its output match our human steering angle. Before training our network, we typically initialize our weights with random numbers. This is why our current weight values just look like random noise. After our images are multiplied by our weights and the results are added together, we're left with 4 numbers that represent our input image. These 4 numbers are then mapped to output steering angles by multiplying by another set of trainable weights, and adding these results together. We can visualize these weights in the same way we visualized our first layer weights. Now, to train our network using Hinton's backpropagation method, we need some cost or loss function that measures how well our network is doing as we train. We'll use mean square error to measure the difference between our network's outputs and our human steering angles, and plot the value of our cost function on our training and testing data as we train. Finally, to see how our network is doing as we train, we'll visualize its predictions on our testing lap. We'll plot the steering angles our human used to get around the track in red, and visualize our network's outputs using a heat map. All right, let's see if ALVINN can learn to steer. As we train, notice that our cost function decreases on both our training and testing data, meaning that ALVINN's predicted steering angles are getting closer to our human steering angles. We can see this directly on our test lap, where we see ALVINN's predictions in yellow converge nicely to our human steering angles. So remarkably, using only images and human steering angles, ALVINN learned to steer around our track. Now, a good follow-up question here is how? How did ALVINN learn to steer? Well, if we have a look at the weights that ALVINN learned, we may gain some insight. Notice that our weights no longer look random and appear to have learned some type of structure. More specifically, if we compare our weights to some of our training images, we see that our neural network has learned a set of lane marker detectors. Remember that when an input image is passed into ALVINN, its pixel intensity values are multiplied by each weight, and these results are added together. When ALVINN encounters an image that is a good match for one of its hidden units, the result of multiplying and adding our image and weight values together will be large, creating a strong signal through this hidden unit, and ultimately steering the vehicle in a certain direction. What ALVINN has learned here are patterns to look for in our data. And what's really remarkable here is that we never told ALVINN what patterns to look for. ALVINN learned to look for lane marker patterns without being explicitly programmed with any information about lane markers. ALVINN successfully drove the NavLab vehicle at Carnegie Mellon, however, only at a top speed of about 1 mile per hour, due to the time required to compute new steering angles as images came in. This slow speed did give the nice advantage of allowing graduate students to write and improve code in the back of NavLab as it drove. And within a few years, thanks to computational speedups, ALVINN was able to drive the second-generation CMU vehicle, the NavLab 2, at speeds of up to 70 miles an hour across various terrains. And more recently, in 2016, researchers at graphics card manufacturer NVIDIA trained a modern implementation of Pomerleau's approach, using a deep neural network and significantly more data than Dean was able to use. The NVIDIA network performs quite well, successfully navigating a wide variety of complex environments. All right, so we've solved half of the autonomous driving problem. We've successfully figured out how to steer using neural networks, so now we just need to figure out the whole gas and brake situation, right? The approach we're using is often called end-to-end, because we're using a single neural network to learn the complete mapping from raw input data to vehicle control signals. Let's hear what some industry leaders have to say about end-to-end deep learning for self-driving cars. First up, Chris Urmson, CEO of Aurora and an absolute giant in the field.
Yeah, I do not believe in end-to-end deep learning as a solution for this anytime in the near term.
Okay, not much of an endorsement for our end-to-end approach. All right, how about Amnon Shashua, CTO of Mobileye? He's been building production-grade driver assistance systems for almost 2 decades now, and has an incredible depth and breadth of knowledge in the space.
So the bottom line here is, from this perspective, the end-to-end system is not workable in the sense of reaching a production-worthy system.
Okay, so maybe we've underestimated the difficulty of this whole self-driving car thing. We began this episode trying to figure out how Dean Pomerleau and Todd Yoakum drove across the US 98% autonomously way back in 1995. Now, remarkably, Pomerleau, the inventor of the first end-to-end learning algorithm for autonomous driving, ALVINN, arguably the most robust and adaptable self-driving vision algorithm on the planet in the late 80s and early 90s, did not use ALVINN to drive across the US in 1995. But why? If end-to-end works so well, why can't we use it to build a production-grade self-driving car? Why can't we teach an artificial intelligence algorithm, like a deep neural network, to drive by learning from huge amounts of human driving data? And how did Dean and Todd make it across the US in 1995? Some answers next time. Thanks for watching. Please consider supporting Welch Labs by backing the channel on Patreon. There's a ton of cool stuff about ALVINN and end-to-end deep learning for self-driving cars I didn't have time to cover here. I've linked a Jupyter notebook below, where you can play with my TensorFlow implementation of ALVINN on some real driving data. Special thanks to Autonomous Fusion for allowing me to use some of their great track data in this episode. Another special thanks to Dean Pomerleau for taking the time to chat with me. Dean was super helpful, down to earth, and a real pleasure to speak with.